record. Okay. So today we have 2.4 polynomial and rational functions. So we will just be looking at the graphs of polynomial and rational functions and finding out their characteristics, such as which way do they open? Do they open up, down, left, right, right, or left? What are their intercepts? And some other fun things. So for now, we get started with a standard form of a polynomial function. So a polynomial function of degree n is a function of the form, and this looks real messy, but this is just a standard polynomial. So what we're trying to say is that you start with the highest power, and then you end with the lowest power and the constant. So that is the standard form of a polynomial. You always start with highest power to lowest power to constant. So that would look something, if I drew an example, we could say that f of x equaled x cubed plus x squared plus x plus 1. That would be the standard form of a polynomial function. It would go from highest power to lowest power to constant. Okay, where the coefficients are all real numbers. Okay. So now we want to look at the end behavior of a polynomial function. So we want to know, what does the graph, whoop, my computer just did something weird. Sure, there we go. Okay. So we want to know how the graph of a polynomial function opens. So the next part is called the end behavior and the leading term test. So all we do is look at the leading term of a polynomial function, and the leading term is always the term with the highest power. So from this standard form of a polynomial, our leading term would be a sub n times x to the n. So that would go right here. A sub n times x to the n. And the leading term tells us enough information, whether it's an even degree or odd degree, and if the coefficient's positive or negative, that will tell us how the polynomial's graph will open. And this all depends on the behavior as x approaches infinity or as x approaches negative infinity. Okay. All right, so I've already drawn out the end behaviors for us. So all we have to worry about is what case they belong to. So for the first two graphs, these cases are when the degree is even. So I'll write that in here. I'll say degree is even. So for case one, if we have an even degree and a positive leading coefficient, so an even degree and a positive leading coefficient, this means that the tails will open up. And what it means to be an even degree are functions such as x squared, x to the 4th, x to the 10th, any even number with a positive leading coefficient. So when we say positive leading coefficient, I can even say 5x squared, where the coefficient is positive and the degree is still even. So no matter what we're given, as long as it's a positive function with an even degree, the tails will always open up. Okay, that's for case one. And that's if the leading coefficient is positive. Okay, case two is still for an even degree polynomial, but the leading coefficient is now negative. Which means that if you have a negative even degree polynomial, your tails will now open down. And this would go for the same examples I have on the left, except all of them will be negative now. So we see that all the powers are even, but here the coefficients are all negative. So for case 2, if you have a negative leading coefficient and your degree is even, then the graph will open down. Okay, and again, we're only looking at end behavior. The reason that these graphs aren't connected is because we are going to figure out how to connect those after this. So the way to connect those tails is by finding x-intercepts and y-intercepts. Okay, so case 1 and case 2 are for even degree polynomials. All right, which means that case 3 and case 4 are going to be for odd degree polynomials. So here I'll say our degree of n is odd. And case 3 says if we have an odd degree, but a positive leading coefficient. And that means, or what an odd degree positive leading coefficient function looks like is x cubed, x to the 5th, any odd power, and I can even say 6x to the 7th, as long as your leading coefficient is positive and your degree is odd, here that's x to the 1st, then your tails will open up and to the right and down and to the left. Okay. And now case 4 deals with an odd degree, but your leading coefficient is negative. So same functions, except they're all going to be negative now. Okay, so if you have a negative leading coefficient and your degree is odd, then your tails will now open up and to the left and down and to the right. All right. So these are the 4 cases that represent the end behavior of even and odd degree functions. Okay. And of course, we'll get more into it. We just want to know how these functions will look. What do their tails look like, depending on their degree? Okay. And down here, we don't have to worry about any of this stuff. Okay. So we're going to use this chart on the next page to help us determine what type of functions we are looking at. But before we do that, let's get into a little more definition about the real zeros of polynomial functions. So with the definition of a zero, this means that a zero is the same as an x-intercept. And remember that to find an x-intercept, you must set your y values equal to 0. So this means that if you have an x-intercept or a 0, this means they are the same exact thing. So by definition, we say if f is a polynomial function and c is a real number, then the following statements are equivalent. C is a 0 of the function. C is a solution or root of the equation when you set f of x equal to 0, or when you set y equal to 0. And C is also an x-intercept of the graph of the function, which becomes the point C0 on the graph of f. So all this definition is saying is that x-intercepts, roots, and zeros all mean the same thing. So whenever we find an x-intercept, we're finding a root, we're finding a 0. So if I gave an example function of that, if I said f of x equaled x minus 2 times x plus 3, then I said find the x-intercepts, you would take f of x or y and set it equal to 0. And you would take x minus 2 and x plus 3, set it equal to 0, and solve for x. Here you would get x equals 2 and x equals negative 3. This means that we have found the zeros of the function, we have found the roots of the function, And as well, we have found the X intercepts of the function. The intercepts would be labeled 2, 0, -3, 0. So by definition, X intercepts, roots, and zeros all mean the same thing. Okay. And now the next definition says a polynomial function of degree n with real coefficients has at most n real zeros. So what this means is that whatever your exponent or degree is on the function tells you how many zeros you're going to have. So if I had the function x squared, this means I would have 2 zeros. If I had the function x to the 5th, this means I would have 5 zeros. So whatever the degree is tells you how many zeros or X intercepts you're going to possibly have. The keywords here are at most, because not all zeros can exist. Okay. And then just another example, let's say I had X to the 10th, I would have 10 zeros. Okay. Now, this last definition says, if f of x is a polynomial of degree n, then the graph of f has at most n minus 1 turning points. So whenever you graph the function, whenever the graph changes direction, those are called turning points. So with that definition, it says whatever your degree is, subtract 1, and that will tell you how many turning points you have. So if we looked at x squared, the graph of x squared looks like this. Well, if it's x squared, this means that I'll have 2 minus 1 turning points. So this means I'll have 1 turning point. So for this graph, this point here is my turning point because the graph changes direction. So for x squared, you would have 1 turning point. Okay, well, let's look at another example. Let's say x to the 5th. If I were to draw x to the 5th, this means I would have 5 zeros or 5 X intercepts. So I'm just going to plot a random 5 X intercepts. 1, 2, 3, 4, 5. And my graph would look something like this. Well, if I have 5 X intercepts and my degree is 5, then for my turning points, I would have 5 minus 1 turning points, or 4 turning points. This means if you look at my graph, I have a turning point here, 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 and here. It's where the graph changes direction. So by the formula and by the graph, we see I have 1, 2, 3, 4 turning points. Okay. So again, your exponent, your degree, your power tells you how many zeros you're going to have, tells you how many X intercepts you're going to have. And then whatever your degree is, you'll subtract 1, and that'll tell you how many turning points the graph has. Okay. So let's go ahead and use these definitions on this whole page to analyze the graphs on the next page. So go zoom in as much as I can. Okay, so for example 1, we're given this graph. It says, what is the minimum degree of a polynomial function that could have the graph? So to answer that question, you can look at how many times you cross the x-axis. So here, we cross the x-axis once, twice, 3 times, 4 times. So if I have 4 X intercepts, this means that the minimum degree I can have is a degree of 4. All right. Or another way to do it is look at your turning points. You have a turning point here, you have a turning point there, and you have a turning point there. So if I have 3 turning points, this means that my degree must be 4, because 4 minus 1 gives me 3 turning points. So that'd be another way to look at it. All right. And then B, is the leading coefficient of the polynomial positive or negative? So now this is where we look at the end behavior chart. So look at our tails of this function. This tail is headed up towards infinity, and this tail is also headed up towards infinity. So here we have an even degree of 4, and we have tails that open up. So if I go back and reference my chart, we have an even degree, and my tails open up. This is going to be a case 1. Case 1 says we are even, and our coefficient is positive. So by case 1, we see that the leading coefficient will be positive. All right. Any questions on that? Okay. So see how we're using the definitions on the first page to answer these questions. Okay. Second one. What is the minimum degree of a polynomial function that could have the graph? Once again, we look at how many times we cross the x-axis. So here's 1, 2, and 3. We have 3 x-intercepts, which means my minimum degree is 3. And then we look at our end behavior. This says, is the leading coefficient of the polynomial positive or negative? Well, that tail goes down, that tail opens up. So we have an odd degree of 3, and we have a tail that opens down and a tail that opens up. So if we go back to the first page, we have an odd degree. So odd degree is case 3 or case 4, and our tail opens down and opens up. This means our leading coefficient will be positive. Okay. And then last one there. What is the minimum degree this polynomial could have? Once again, we look at how many times we cross the x-axis. 1, 2, 3, 4, 5, 6. This will have a degree of 6, which is even. And then we want to know, is the leading coefficient positive or negative? Well, these tails open down. So we have an even degree, and my tails open down. Well, above, we had an even degree, and my tails opened up, which means the leading coefficient was positive. So now, if we have an even degree and my tails open down, this means that our leading coefficient must be negative. Okay. Oops. All right. Any questions on those 3? Once again, we are referencing the definitions on the very first page. All right. Number 2. Again, using the definition from the first page. This says let f of x equal x cubed minus 8x squared plus 9x minus 1. What is the maximum number of x-intercepts for the graph of f? So remember, that if we want to find the maximum number of x-intercepts, which also means the maximum number of zeros, we look at the leading term, the term with the highest power. And here, that term is x cubed. And now, remember that the highest power tells you how many x-intercepts you have. So since our degree is 3, this means that we're going to have 3 x-intercepts. Okay. Now B, what is the maximum number of turning points for the graph? Well, the turning points formula is you take your highest degree and subtract 1. So this means we would have 3 minus 1. So we would have 2 turning points. Make that more of a T. Okay. And then C, is the graph increasing or decreasing as x gets infinitely smaller? Okay. So what that means is we're looking at end behavior. So we have, first off, we have an odd degree with a positive leading coefficient. So this means that, let's go back to the very first page. And now we see that we have an odd degree with a positive leading coefficient. So we're looking at case 3. So what those questions are saying is that as x goes to negative infinity, where are my y values going? So as x goes to negative infinity, my y values are also going to negative infinity. And then as x goes to positive infinity, my y values are also going to positive infinity. So that's what case 3 is about. Okay. So to answer this question, is the graph increasing or decreasing as x gets infinitely smaller? Well, we see that from the chart above, that as x went to negative infinity, your y values are going to negative infinity. So this means we decrease here. And then I can draw a little graph here to represent both of these answers. And then, is the graph increasing or decreasing as x gets infinitely larger? So as x heads towards infinity, your y values will get larger. Okay, and this is all represented by the cases. All right, next one, 3. Let f of x equal negative 7x to the 4th minus 2x plus 41. Again, look at the leading term. It's the one with the highest power. So it's going to be negative 7x to the 4th. The degree tells us how many intercepts we're going to have. So if the degree is 4, this means we have 4 x-intercepts. Okay. And then B, what is the maximum number of turning points? Well, you take your degree and subtract 1, and we'll get 3 turning points. Okay, now we have an even degree polynomial with a negative leading coefficient of negative 7. So that's going to be a case 2, which means that our tails will open down. Okay, so to answer the next 2 questions, it says, is the graph increasing or decreasing? So we're saying, are the y values increasing or decreasing as x gets smaller? So as x goes to negative infinity, we see that our y values are also going to negative infinity, which means they are decreasing. And then the next question says, are your y values increasing or decreasing? Are they getting larger or smaller as x goes to positive infinity? Well, we see that this tail is also headed towards negative infinity. So this means that they are also decreasing. Okay. So we're using those cases to answer these questions. And then example 4, let f of x equal negative x to the 5th plus 5x to the 4th minus 12x cubed plus x minus 16. What is the maximum number of x intercepts? Again, we look at the leading term with the highest power, which is going to be negative x to the 5th. The power is 5, which means we get 5x intercepts. Next is turning points. So you get 5 minus 1, you get 4 turning points. And now, let's look at our case. If we have an odd degree of 5 with a negative leading coefficient, this means my graph is going to open, what's I do? Oh yeah, sorry. This graph is going to open top left to bottom right. Okay, so to answer these questions, we say, are your y values getting larger or smaller as x approaches negative infinity? Well, if x is going to negative infinity, these y values are getting larger. So this means that my y values will be increasing. And then it says, are your y values getting smaller or larger as x heads towards infinity? Well, these y values are definitely getting smaller towards negative infinity, so they are decreasing. Okay. And those are the characteristics of polynomial functions. So if you just know the leading term, and whether it's positive or negative, then you can find the x intercepts, you can find the degree, and you can find out the end behavior of the polynomial. All right. Any questions on that page? All right. So those were polynomial characteristics. Now we get into rational function, the characteristics of rational functions. So remember, rational function is just a fancy word for fraction. So a rational function is given by a polynomial over a polynomial. So there we have n of x over d of x. And a rational function can also be represented in this standard form, where again, the numerator is a polynomial from highest power to lowest power, and the denominator is a polynomial from highest power to lowest power. Okay, and I guess I could give a good example of that. Let's say I had my rational function and I had x cubed plus x squared plus x over 2x to the 4th plus x cubed plus x squared. This would be a rational function where you have a polynomial in the numerator and a polynomial in the denominator. And they all go from highest power to lowest power. Okay, now remember, with rational functions and fractions, the denominator can never ever be 0. So the denominator can never be 0. Okay. All right. And then the vertical line, x equals a, is called a vertical asymptote of a graph if the graph approaches the vertical line. So what this means is, with rational functions, we're going to come across a definition of an asymptote. Rational functions are the only functions with asymptotes. They'll have a vertical asymptote and a horizontal asymptote. So vertical asymptotes come from the domain of a rational function. We can even keep it simpler and say that vertical asymptotes come from the denominator of a rational function. So in order to find a vertical asymptote, you must set the denominator equal to 0 and solve for x. So this is what a vertical asymptote looks like. Let me go ahead and draw a nice little graph. I'll have some function or some line called x equals c. And with a rational function, when you graph it, you can never, ever cross a vertical asymptote. So at this vertical asymptote, one tail of my function could go to negative infinity, and another tail could go to positive infinity. But a vertical asymptote can never, ever be crossed or intersected. Okay, and again, to find a vertical asymptote, take your denominator, set it equal to 0, and solve for x. Okay, the next type of asymptote is called a horizontal asymptote. So a horizontal asymptote is another line that a graph approaches, but this time you may be able to intersect a horizontal asymptote. So I'll draw a, let's see, I'll do it like this. Here's my horizontal asymptote, and it's given by the equation y equals L. If I were to draw my function, then we would get really, really close to it and possibly intersect it or never even touch it. But horizontal asymptotes can be intersected. The only type of asymptote that can't be intersected is a vertical one. Okay, so keeping everything really, really simple, an asymptote is a line that your graph will approach, but will never touch. So you get really close, but you'll never touch. A horizontal asymptote, you may intersect on that possibility. But again, this is business math, so we don't get too crazy with this stuff. Okay. So with horizontal asymptotes, we have a couple of rules. We have 3 rules to find a horizontal asymptote. Rule number 1 says that if the degree of the numerator is smaller than the degree of the denominator, then y equals 0, or which is also known as the x-axis, will be the horizontal asymptote of your graph. So like I said, I'll draw examples of these. Let's say I had a function that was x plus 1 over x squared minus 2. The degree of the numerator is 1. The degree of the denominator is 2. So by rule 1, since the degree of the numerator is smaller than the degree of the denominator, we automatically get a horizontal asymptote of y equals 0. Okay, that's rule 1. Easy. If the degree of the numerator is smaller than the degree of the denominator, y equals 0 is your vertical asymptote. Okay. Rule number 2. If the degree of the numerator is equal to the degree of the denominator, then y equals the leading coefficients of the numerator over the denominator is your horizontal asymptote. So a good example of that one. Let's say I had y equaled 2x squared minus 1 over 4x squared plus 2. Here, my degree in the numerator is 2. My degree in the denominator is 2. These degrees are equal. So that means since the degrees are equal, rule 2 states that your horizontal asymptote will be the leading coefficients over each other. So you'll get 2 over 4, or better yet, that'll be 1/2. Okay, All right. So a common mistake students make is that, let's say for rule 1, you're like, oh yeah, the horizontal asymptote is y equals 0. Well, students like to say the horizontal asymptote is just 0. That would be incorrect to write because 0 is just a number. Y equals 0 is an actual equation. That's the graph of a line. So make sure you write it as y equals 0 and not just 0, because 0 is a number. Y equals 0 is an actual line. Don't make that mistake. Okay. And then 3, if the degree of the numerator is bigger than the degree of the denominator, then we no longer have a horizontal asymptote. We have something called an oblique or slant or linear asymptote, which will be in the form of y equals mx plus b. And this only happens if the degree of the numerator is bigger than the denominator by 1. And the only way to find this horizontal asymptote is by using long division, which we won't do in this class. But I'll just show you an example real fast. Let's say I had y equal 2x squared minus 1, and then the denominator was x plus 1. Here, my degree is 2. In the denominator, my degree is 1. So this means that the degree of the numerator is bigger than the denominator by 1, which means we no longer have a horizontal asymptote. We have an oblique asymptote, and the only way to find it would be to use long division. All right, but I wouldn't worry yourself with those. We're not going to do long division in this class. Okay, those are the 3 rules for horizontal asymptotes. They are quite simple to remember, but you get to use your notes on the test anyway, so you'll be fine. Okay. So first example below says find the vertical asymptotes of the rational functions. So here we want vertical, and remember that to find vertical asymptotes, I said vertical asymptotes come from your denominator and your domain of your given function. So for number 5, to find this vertical asymptote, the first thing I'm going to do is find the domain of it. And to find the domain of a rational function, you take the denominator and you set it equal to 0. And now we're going to solve for x. I'll move that 4 over, and then I'll square root both sides. Here we'll get x equals plus or minus 2. But we know that since this is in the denominator, x cannot equal these 2 numbers because it will make the denominator 0. So here's our domain. And if you have your domain, here's the easy money. You have your vertical asymptotes. My vertical asymptotes are going to be x equals -2 and x equals 2. Easy money. If you have your domain, you have your vertical asymptotes, and they come from the denominator of your function. Okay. Again, do not make the mistake of saying vertical asymptotes are 2 and -2. These are just numbers. X equals is a line. Do not make that mistake. It will count it wrong on my math lab. All right. 6, same thing. Find the vertical asymptote. First thing we do, find the domain. Take 6x plus 18, set it equal to 0. Move the 18 over, divide by 6, and x will equal -3. But we know this can't happen because if x is -3, the denominator becomes 0. Okay, and once again, easy money. Vertical asymptote is x equals -3. There we go. So that is how you find vertical asymptotes. You take your denominator, you set it equal to 0, and you solve for x. That's it. Okay. All right. Next examples are finding the horizontal asymptotes of the rational function. So here's where we're going to look at the rules 1, 2, and 3 for horizontal asymptotes. And we're going to look at the degrees of the numerator and the denominator. All right. So for 7, we have 3x cubed over x to the 5th. I'm not going to read out the rest of it because, again, we're only looking at the leading terms. Okay. So in my leading terms, the degree of the numerator is 3. And then the degree of the denominator is 5. The degree of the numerator is smaller than the degree of the denominator. So n is smaller than m. 3 is less than 5. This means that this is rule number 1, where your horizontal asymptote is going to be y equals 0. That's it. All you have to do is look at the degrees. Okay. And then number 8, same thing. Just look at your exponents. And for number 8, here my degree is 2. Denominator, my degree is 2. So the degree of the numerator is 2. Degree of the denominator is 2. This means that our degrees are equal, which means this is a rule number 2, where it states that your horizontal asymptote will be y equals the leading coefficients over one another. So you'll have 6 over 2 or y equals 3. I don't need so many colons, right? Oh. There we go. And then number 9, the degree of the numerator is 3. Degree of the denominator is 2. Numerator is 3. Denominator is 2. Here, the numerator is bigger than the denominator, which means that this is going to be a rule number 3, which means we no longer have a horizontal asymptote. You get an oblique asymptote, which the only way you can find is by using long division. So I think for my math lab, it only asks you to find horizontal asymptotes. So we say no horizontal asymptote. Okay, and that's how you use the rules for horizontal asymptotes.
I have a quick question about
Go
number
ahead.
8.
Go ahead.
How did we get the 3 again, like at the end?
Because you take the leading coefficients over each other, right? So the leading coefficient of the numerator is 6, and the leading coefficient of the denominator is 2.
Oh, we divided. Oh, I'm sorry. I didn't realize
You're
that.
good. You're good.
Okay, thank you.
Mhm. All right. Everybody else good? Okay. So now, putting it all together, we want to list all the asymptotes of the graph and then find a function that will represent this graph. So the first thing we look for are vertical asymptotes, which means look for your vertical lines. And we see that we have a vertical asymptote at the x value of -2 and the x value of 4. So what we'll write here is my vertical asymptotes are x equals -2 and x equals 4. Okay. And then we look for the horizontal asymptote, which means you look for a horizontal line. Well, the only horizontal line here is at that value of -2. So since it's a horizontal line, our asymptote, horizontal asymptote, is going to be y equals -2. All right. So all we have left to do is find a function that would represent this. So remember that vertical asymptotes come from your denominator. So if I were to take my vertical asymptotes and put them back into polynomial form, and that means, let me just go ahead and rewrite these real fast. X equals -2 and x equals 4. If I were to put these into polynomial form, this means that I would add the 2 back over to the x, and I would get x plus 2, and I would subtract the 4 back over to the x, and I would get x minus 4. Now, go ahead and FOIL this out, and we'll get x squared minus 4x plus 2x. So you get x squared minus 2x minus 8. Now we match this to the problems above, and it looks like it's either going to be, because we have minus minus, it's going to be A or C. So B and D are out. Okay. And now, since we've taken care of the denominator, we now must take care of the numerator by using the horizontal asymptote. So if we get a horizontal asymptote of -2, this means that we are using rule 2 of the horizontal asymptotes. And rule 2 states that your degrees must be equal. So let's go ahead and look at our functions A and C. Here in A, I have a degree of 2 and another degree of 2. So by rule number 2 of horizontal asymptotes, I'll say this is for A, we would get y equals the leading coefficients over one another. So the leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 1. So I'd get a horizontal asymptote at y equals +2, which means that A is out because we're looking for a horizontal asymptote of -2. And just to show you how that works, if we looked at C, the degree is 2, the degree is 2. So the numerator is 2, denominator is 2, which means you'd put the leading coefficients over each other. and you'd put -2/1, which gives me -2. So this means C is the only one that checks out. So this is the function that represents this graph. All right. Any questions on that?
Sorry, I'm a little confused on how we figured out the numerator.
The numerator. We're doing it by the rules of the horizontal asymptotes. So, so in C, what is the degree of the numerator?
I don't know why I just forgot what our numerator. The numerator is the top, correct?
Exactly.
Oh, okay. The degree
So
of the top is 2.
is 2. Now look at your denominator. What's the highest degree down there?
2.
Are they equal?
Yes.
Then by rule
So
number
that's-
2
okay.
of the horizontal asymptotes, right? You
Mhm.
put the leading coefficients over each other.
Okay.
So -2/1 will give me -2, which is what we wrote for our horizontal asymptote.
Gotcha. I'm just forgetting about the rules. Thank you, sir.
Oh, good. You're good. All right. Any other questions on that one? All right. All right. Last one. A company manufacturing surfboards has fixed cost of $400 per day and total cost are $5,400 per day at a daily output of 20 boards. Assuming the total cost per day, C of X is linearly related to the total output per day X, write an equation for the cost function. All right. So here, I think they're giving us 2 points. So we're gonna have to create a cost function from those given 2 points. Okay. Zoom in. So this says we have a fixed cost of $400 per day and a total cost of $5,400 per day at a daily output of 20 boards. Okay. So the first point they're giving us says that even if we sell 0 boards, we're going to pay $400 per day. The second point says if we sell 20 boards, our cost is going to be $5,400 per day. Now, we've done this before. Remember that if we're given 2 points, we can find the slope between 2 points. And if we have a slope and a point, we can find the equation of a line. So the first thing we're going to do is find the slope between these 2 points. So I'm going to label these as x1, y1, x2, y2. And I'm going to look at slope first. Remember the slope formula is y2 minus y1 over x2 minus x1. So plug in our y2 of 5,400 minus my y1 of 400 over x2, which is 20, minus x1, which is 0. This will give me 5,000 over 20, or 5,000 over 20. Take a 0 out. I think that's 250. Yes, 250. All right, so here's our slope. Okay. Now, to find the equation of the line, to find the equation for our cost function, Well, we're going to use the point slope formula. Y minus y1 equals m times x minus x1. And my slope is m, and I already labeled a point 0 and 400 for x1, y1. So we're just going to plug in everything we have. You're going to get y minus y1, which is 400, equal to my slope of 250 times x minus x1, which is 0. Go ahead and distribute that 250. And you'll have 250x minus 0. So just 250x. Add the 400 over, and we get 250x plus 400. Okay. And there's the equation of our line with the given information from the problem. This wants us to write it as a cost function. So all we're going to rewrite it as is c of x equals 250x plus 400. All right, there's step A. Any questions on that one? So remember, given 2 points, you can find the slope. If you have a slope and a point, you can find the equation of a line. That's all we did here. We did this back in 1.2, I think, section 1.2. So long ago. Okay. Now, moving on to B. The average cost per board for an output of X boards is given by the formula C bar of X equals C of X over X. Find the average cost function. So this formula they're giving us is called the average cost function. And in order to find the average cost function, well, the formula already has it laid out for us. You take the cost function and put it all over X. So we take the cost function we just found and put it all over X. This is all that it wants. So we say C bar of X is equal to the cost function we found in step A, 250x plus 400, and you put it all over X. That's it. That's the average cost function. Okay, that was bad. Next, sketch a graph of the cost function, including any asymptotes for the X values 1 through 30. So here we're going to make an XY chart. And we're going to choose the values it's giving us. It's telling us what X values to choose. This says choose the X values 1 through 30. So I'm going to start at 1, but then I'm going to go by 5s. 5, 10, 15, 20, 25, 30. Okay, and now I'll go ahead and use Desmos, our best friend. My laptop wants to cooperate. All right, so we're sketching the average cost function. So I'm going to put in our average cost function, 250x plus 400 all over X. And then I'm going to use the table feature and type in the numbers that I've written over here. 1, 5, 10, 15, 25, and 30. Oops, here we go. Okay. And I get 650, 330, 290, 276.67, 270, 266, and 263.33. Okay, so there's my XY chart, and this should say average cost function. That's what we're graphing here. Okay, now back to this. I'm going to draw my intervals for my x-axis. This will be 1, and then 5, 10, 15, 20, 25. No, so I'll just make this 5, 10, 15, 20, 25, and 30. There we go. And then my y values, highest they go is 650. So let me go by 100, sure. 100, 200, 300, 500, 600, and 700. Okay. And now 1 and 650 right there. 5 and 330 around there. And then 10 and 290 right around there. 15 and 276 still right around there. And then 20 and 270 still there. It's just a sketch. And then 25 and 266 still in that area, and 30 and 263. Okay. So here's what our function looks like. Actually, it stopped at 30. It says 1 through 30. There it is. Okay. So this said include any asymptotes. So if we look at our average cost function, let me zoom in on this. If we look at our average cost function, which I'll rewrite right here. Here we go. C bar of x equals 250x plus 400 over x. The first thing we can look at is a vertical asymptote. So to find that, remember you find the domain. Here, we would just take the denominator and set it equal to 0. So you automatically you'd get x equals 0, which can't happen, which means that my vertical asymptote is x equals 0. So there's my vertical asymptote. Okay. And then for my horizontal asymptote, well, we look at the average cost function and we look at the degrees. Here, the power of the numerator is 1. Here, the power of the denominator is 1. This is going to use rule number 2. Since the degree of the numerator and the degree of the denominator are the same, they are equivalent, you put the leading coefficients over one another. So here, my horizontal asymptote is going to be y equals 250. All right. And now if I wanted to draw this, 250 would be around here. Like I said, it's just a sketch, but this would be y equals 250. Okay. And of course, we could look at a better sketch. Let me see. Let me go ahead and change this intervals. So my x-axis will start at 1 and end at 30. My y-axis will start at 0 and end at 650. There we go. All right, so we only look at this part, and then I have a horizontal asymptote at y equals 250. There we go. Now that one looks way better than my sketch, but I'm showing you this so we can answer the final question. It says, what does the average cost board tend to as production increases? Well, that means look at the horizontal asymptote of your average cost function. We see that as costs, as we produce 30 boards, we see that cost starts to get closer and closer to that horizontal asymptote of 250, as you see on my graph and on the graph to the left. So whenever you see these words, average cost per board tend to, come on. Average cost per board tend to, this means just look for the horizontal asymptote. And the average cost is going to tend to $250 per board. So the more we make these boards, the more the cost will decrease, assuming that somebody is buying them. So we'll say average cost is $250. There you go. All right. And that is 2.4. Any questions on this page?